See, you forget all sorts of things. But the real place I want to start here, before we move on to RC circuits, is looking at reviewing our rules for capacitors and resistors, right? So what we've done is we've created these rules for how to add these objects in series and parallel, but what we don't want to lose track of, right, is that we've learned to identify when circuit elements are in series and parallel, as really seen in some of our example circuits, right? Like we saw in our first example circuit, we know that R3 is in parallel with R2, but R2 is neither in parallel nor series with R1. We have very firm definitions there. We also know how to use the loop law to make sets of equations to solve systems. And we have a lot of machinery to analyze these DC circuits. And we did that example. But we did the ammeter and the voltmeter before, and you also have that in the lab. And now we want to go to our RC circuits, okay? And RC circuits is now, this is kind of fascinating because we've talked about resistors, we've talked about capacitors, but now we can see sort of the interesting things that happen together, and we can discuss the difference between a battery and a capacitor, because they look like they're the same thing, except they run very differently, all right? As I said before, batteries react on electrolysis and chemical reactions, whereas capacitors, and that leads to charge separation or the storage of charge. Capacitors store charge completely electrostatically. And I want you to notice our switch here, which I tried to build with the FET simulations. That was an epic fail because they only have they don't have a dual switch. They only have an off-on switch. This switch is, you can almost think of it as a three-state switch, right, with this being off. But if we look here, and we have the switch goes to A, we have this circuit, right? Well, let me get the hand. We float on, we go through, and we charge up the capacitor. This causes a delay, and then the line is finished. Now, if we do the switch to the other one, right, once that capacitor is charged, now the capacitor can discharge. The current will flow, or it'll sort of act as a delay. Current will start floating and start neutralizing, discharging the capacitor. And then once it's uncharged, then you'll have, it'll be, the current will stop flowing. So let's break it down one by one. And we want to recall, let's see here. I feel like they're missing a step. No? That's making me mad. All right. So I guess when you look at this circuit, I guess what I want to do is I want to apply the loop law. I want to show you at least where some of this comes from. So let's make one circuit. So we're going to talk about charging the capacitor. So let's take a look at the, let's use the loop law and see if we can make sense of some of this equation. Because right now, this looks like a bunch of magic, honestly. And I don't like magic in my physics classes. So let's see if I cannot mess this up. If I mess it up too bad, I will fall back on magic, which some of you may be excited to see. I'm not. It'll mean I had a bad day. Okay. So as we go through our loop, we're going to start from point A and go back to point A. And we're just going to assume the current goes around like so in our circuit. Now, when we do this, we'll start at the resistor. We're going in the direction of the resistor. So we'll have I, R, right? And when we look here at the capacitor, we're going to also have what's essentially a voltage drop, right? But we'll call that I equals or minus The voltage of the capacitor is Q over C. All right. And then when we get back here, we'll get to the battery. We'll go through that positively. Epsilon. And from there, this is going to work. I'm always happy when things work like I think they're going to. So we don't need magic. It still might seem like magic, but we get back to our point and go to 0. Now, you might look at this and go, wait a minute, Professor Toland, what in the world does any of that nonsense have to do with these equations that are listed on this slide? Well, I'm going to show you, they kind of give it away, and I'm going to recast it. Now, they give you a Q value and an I value based on E being the derivative of T, and then from there you can derive the voltage. So it's sort of easy if you accept. The only magic step really is this one. But where does this Q come from? So it actually comes from recasting our equation like so. This is going to be equal to, I'm gonna move the minus terms to the other side. I'm gonna move everything to the other side actually, because that'll make me happy. Let's mess that up. So if we move everything to the other side, we get dq dt times r, right? Because I is equal to dq dt, minus q, that's going to be times 1 over c, or actually that's going to be a plus, minus epsilon, or minus squiggle, and that's going to equal 0. Now this is what is called a first order non-homogeneous. Actually, is it non-homogeneous? It might be homogeneous. It might allow for this because I don't think there's a forcing term in Q, but it's definitely a first order differential equation. All right, and basically this is, and as this is kind of fun because I got to the same point sort of with physics 1 earlier today. And so what you can see now is we're sort of ripping off and seeing some of the real machinery behind the physics, and why the loop law is important. Because the loop law, as we saw, is sort of a way of invoking energy conservation. And energy conservation allows us to create differential equations and solve for the dynamics of those equations. A lot of times we have to use computers to model them because it can be complicated. But this is looking at it at a bit of a deeper level. All right. So if you take this Q function, all right, and you take Q equals this, and you plug it, you take its time derivative, which you're also given here. All right, you can plug it into this equation, and you can actually solve and see that when you do that, this side will equal 0. All right, and when you do that, that is one method of solving a differential equation, is plugging the solution in. Now, that's going to seem weird to my non-math, to those of you who are used to doing math a certain way, but what you have to understand is that differential equations is sort of where mathematics straddles both the abstract proof part and the computation part. And what I mean by that is part of the mathematics of differential equations is ensuring that if you find a solution, it's unique and that it's well defined and other things like that. That there aren't a bunch of other solutions, and that that the solution you do find will work in a very happily behaved domain. So as engineers, you will very rarely encounter that type of math, but that's what math starts to be, right? And so all we're saying is if we can show this as an equation to this differential equation, which you can, then you're ensured a whole bunch of properties, and that's how that really works. And a lot of people spend a lot of time guessing at the solutions to these equations. And this equation you can build from the loop law, okay? And it's not quite as clean as the discharging one. That one's a lot easier, but you can look at that. And now let's look at some of the properties. Now that we've seen the equation, let's look at some of the properties of the solution. All right, or let's look at the behavior. So we can see in our graph that Q, we have Q versus T on the capacitor, right? So we see that it takes some time in milliseconds for the capacitor to fully charge. All right, but much like the virus, hopefully, it will asymptotically approach a maximum value that it can't exceed. All right, and that will be our total charge. So you'll notice that if you look at the solution here, I want you all to take the limit, and by the limit I mean don't be so horrible, but look at what happens. Plug in t equals 0. Hold on. Plug in t equals 0 and tell me what you get. What does q equal at t equals 0? For the one right next to it. This one. What is q? We're just looking at q right now. Are you sure? If t is equal to 0, that's e to the minus 0. What's e to the minus 0? Ah, good, 1. And 1 minus 1 is 0, so at t equals 0, q equals 0. All right? And that makes sense with our graph. If we look at our graph, we'll notice that we start at 0, and as we understand the system, we should be okay with this because we're charging up a capacitor, which the implication there is that there is no charge at the beginning of the process. So now let's look at the other extreme, right? Technically, you have to take the limit, but here's where I'll go back to being cavalier. What happens as t approaches infinity? Basically, slap the infinity in there and tell me what happens. Then what's q equal to? No. It's e to the minus t. Right, CE. So if you look at e to the minus t over whatever it is, RC, right? As t gets bigger, is this get bigger or smaller? It gets smaller, much smaller, right? So at infinity, it becomes identically 0, right? And it doesn't matter. And then q, that means this part goes away to 0. And that means that q is equal to C squiggle times the EMF. All right? Does that make sense? Now, I wanted to use this area. I'm going to clear because I wanted to use that area here. Now, looking here, we can look at the current as well. And we can see here that at t equals 0, right? So right when we start, we'll have I equals. Now this makes sense too, right? Because we'd expect that the maximum charge will flow into the capacitor. That means the maximum current. And then, of course, once the capacitor is charged, we shouldn't expect current to flow at all. And in fact, we see that at t equals infinity, I equals 0. Okay? So you'll notice now that we have a time dependence in our charge and our current, and we'll be able to solve for the voltage as Q over C. If Q is time dependent, right, you get this sort of compact expression for the voltage as also a function of time. Now, the other interesting thing is you'll notice that the time is over RC, okay? And RC is defined as the time constant. So that is the time at which you fill up, you're at that 1 over E. So I think it's like you lose, I can never remember whether it's, you know, they have it here, they have the time, for instance, here in terms of time constants. So I think it's you get 75% and then another 75% and so forth and so on of growth. right? So that's 2 time constants. No, this is milliseconds. You'd have to do the 1 over e to figure it out. But basically, what you can do is what's interesting about capacitors is you can pick the capacitance and resistance value, right? So that you can design how long it takes to charge and discharge. All right. So sometimes, so what capacitors can do that batteries can't do necessarily is charge all at the same time and discharge very rapidly. And in fact, some people are I believe they've tried to create these things called supercapacitors, in which you can figure out, I believe you can do one quickly and the other slowly, right? Do the capacitor that can charge quickly and discharge slowly, then you could have you could essentially charge your battery in a couple seconds and have it last a couple hours, right? That's ideally the idea behind something like that. So that's pretty cool. But then we want to look at the discharge case, all right? And you can do the same thing, and you'll notice with the discharging case, you can plug in the same things, but now you have the switch. That's not going to work. You can have the switch set to here, and that takes this part. You can take that part out of the circuit, right? So when you're doing your analysis, you're only going to have the capacitor and the resistor. And here, you'll notice you get the a decay now, right? You're discharging the capacitor. Okay. So the current kind of works the same way here. As you're, but then of course, after you discharge the capacitor, it's just a circuit with a discharge capacitor and resistor, not connected to anything. Nothing's happening, right? The current starts high and goes low. Okay, so so a capacitor that is being charged initially acts like an ordinary connecting wire relative to charge current. A long time later, it'll act like a broken wire. All right. So basically, the circuit goes from closed to open. Is essentially what it's about. And electricity can't flow through open circuits. Okay, so that pretty much finishes us off up on circuits. Does anyone have any questions about that while we load the? So questions? Well, if you miss out some stuff, remember we're recording, so it's not worth it to go all the way back. So watch the first couple minutes of the recording. You can catch up anytime. Okay? So let's see. So we want to go to the new chapter where everything is nice. Oh, right, I have to hit share now. Okay, nope, that's the wrong one. Oh, I see where I can keep getting messed up there. Okay, so we're going to try and combat some of the wordiness from magnetic fields, but I'm not sure that we are going to succeed necessarily. But you're going to notice the definitions start out at sort of a high stress level. And you'll see that from right when we define magnetic fields, you'll see that they're defined with a cross product, everyone's favorite vector operation. Not only that, but a scaled cross product, no less. All right. We're going to, let's look at our symbols. We can define a magnetic field B. So unlike the electric field, which was given with an E, the magnetic field will be given with a B. It's a vector quantity that exists when a magnetic force on a charge moving with a velocity, exerts a force on a charge with velocity v. So basically, what we're going to find is that magnetic fields require charged particles moving with a velocity in a magnetic field, and that will create a magnetic force. you can get the magnitude of B in terms of the force and QV over here, and that's kind of cute and all. But what we really want to start with is this expression, right? Where FB is equal to QV cross B. But of course, the magnitude of that force is equal to the magnitude of Q times V times B times sine phi. That's what we can do, which is the angle between the velocity vector and the magnetic field vector. Now, of course, this is the magnitude of the cross product, right? This is what we've done before. And of course, wherever we have cross products and magnitudes, we must review everyone's favorite part of Physics 1 and statics, the right-hand rule, right? So if you look here, you have a vector V. I was just going to put my hand on the board, and I realized no one can actually see me if I put my hand on my screen. So we're just going to do the best we can. But notice we have a hand here, and we first start with B. So if you want, put your hand like near your screen. And then you want to close your hand towards that vector B. And then you stick your thumb up. That direction of your thumb gives you the direction of V cross B. Okay? So you got V, V cross B, V cross B. All right? Now, what's it saying here about F force on a negative particle? So the force on a positive part, and this is the other thing, is we have to look at take into account electrons too. So if we're looking at a proton, we're fine, but if we're talking about an electron, we have to change the sign. All right? And maybe that means the book wasn't wrong. Well, we'll get there. All right. No, that's incorrect. So we not only have to keep track of everything, we have to look at the sign of the charge as well, because that could just flip the force vector. Okay, after we look at it. So first we have to apply the right-hand rule and look at V cross B, and then V cross B will be the same direction as the force for a positive particle. It'll be in the opposite direction for a negative. Oh, that's why I got that wrong. Okay, so actually, all right, now I see everything. Okay. So the figure here shows 3 situations in which a charged particle with a velocity v travels through a uniform magnetic field. In each situation, what is the direction of the magnetic force on the particle? So, first one is pretty easy, right? You put your hand on V, and if you do that, like so, and you close it, you're going to get, it's pointing in the positive Z direction. Good. B can be a little tricky though, because with B, and I mean tricky because if you're like me and and start getting obsessed and thinking the checkpoint asks for V cross B, you'll get mixed up, because V cross B is definitely going to be in the positive X direction, but the sign is negative, so we have to flip, right? So once we do that, we can do V. You can put your hand down in V, flip towards B, and you'll get that positive X direction. But now you have to ask yourself, it didn't ask for V cross B, it asked for FB. So you have to ask yourself, do I have a negative charge or a positive charge? You'll notice you have a negative charge here. So that means you got to flip that direction of B. Okay? And that will, and then of course here for part C is a little trivial. All right, because the angle between these two is 180. And so the magnitude of FB, right, is going to be 0, because these are anti-parallel. And sine of 180 equals 0. Remember, the magnitude of FB equals Q V B sine phi. Okay? So remember that from the cross product. All right. But now we want to try and visual a magnetic field. We want to be able to measure the not measure, that would be nice, that would be lab. But we want to be able to discuss the magnetic field and get a visual sense of it. All right, so let's take a look here at our visual slides. So you'll notice with the magnetic field, it sort of looks like you would expect it to. And we're actually going to do something that I don't think we maybe should do. But the whatchamacallit, oh lordy, what was I going to say? But it's going to be a little confusing because when we start talking about the magnetic field and the properties of it, at first we're going to talk about permanent magnets. Now, I guess one of the weird ironies of life is that permanent magnets are some of the hardest to describe physically. You require a lot more machinery than this class, but permanent magnets are the easiest intuitive way to understand the magnetic field and magnetic forces. But breaking them down into like what's going on is very difficult. Whereas we will talk more about current-based magnets using currents to have electric field, which is not something you do in your everyday life, but probably some of you might. But in that sense, it can be, you know, a little unintuitive why we're doing it that way. But this was the easiest way to quantify and study magnetic fields in the lab in the 18th and 19th centuries. So what we're looking at is a bar magnet, and we'll notice that magnets, much like you note, have north and south poles. Magnets always have north and south poles, which makes them natural dipoles. So unlike charges, which can be independently negative or positive, magnets always have north and south poles. There's no such thing as a north pole only or south pole only magnet. All right? And you can see that these field lines will always sort of close back in on themselves. All right? This actually makes Gauss's law for magnetic fields so trivial that we'll only look at it once now, and then once when we do it for Maxwell's equations. But basically, the integral, the closed surface integral of B dot dA, that is around a closed surface around a magnet, is just always going to be 0. That makes that easy. So, some things to notice is that the direction of the field will just be tangent at any given point. So if you pick a point on the magnetic field, you just draw the tangent line, and that will give you the direction of the field at that point. You'll notice that the direction of the field does change as you traverse the field, though. It can change quite a bit. It's going in opposite directions here. And much like electric field lines, you'll notice that away from the magnet, the flux lines are very far spaced apart. So here, you notice that you have to go quite a distance to get to these 4 magnets. This might be better with the pencil, right? So to cross 4 flux line, you have to make your line, blue line, that big. But over here, to cross the same flux lines is a much smaller line is required. That means that closer to the magnet, the field is much stronger. And you can represent magnetic field strength with the number of flux lines, just like you could the electric field. Now, with charges, we had like charges repel, or no, like charges repel and opposite charges retract. We're going to have the same thing going on here with poles. So opposite poles, north and south poles, attract. You can see that along the field lines, right? They close in. The field lines start at north poles and they end at south poles. And like poles will repel. And if you ever played with magnets when you were smaller, or even yesterday, maybe even earlier today, you will have seen that they'll want to come together, but if you flip them around, they'll spring apart. All right, and that's essentially what you're seeing there. So yeah. So are there any questions about the basics of magnets thus far? Okay. So if you want a descript nature or of the definitions, I've decided that I'm not going to just go over all these lines. I'll talk about it, and I didn't miss anything. So we'll just go on. Now, crossed fields, the discovery of the electron. So now we sort of get to some of this interesting stuff, right? It might be a little anticlimactic because there's a lot of word barf here. I couldn't find a good way to take it out, but basically what you're looking at here is a modern version of J.J. Thomson's apparatus for measuring the ratio of charge to mass, or mass to charge, and that was one of the big results of the whatchamacallit, the what's that century? The 19th century. You could basically, you have a filament that can fire these charged particles, right? And you can put them through a magnetic, there's a B field through magnetic field and an electric field in this capacitor, all right? And so what happens is, let's just read through this. An electric field E is established by connecting it. Okay, we know that, that's fine. So that gives you this battery. The magnetic field is set up by means of a current in a system of coils, not shown, that's nice. And the magnetic field is shown into the plane. So you'll notice that those X's mean it's going into the page. All right, so now if a charged particle moves through the region containing both an electric field and a magnetic field, it can be affected by both an electric force and magnetic force. When the two fields are perpendicular to each other, they are said to be crossed fields. And if the forces are in opposite directions, one particular speed will result in no deflection of the particle. So let's not be an asshole and actually, oh, I'm not supposed to swear like that on the recording. Let's not just pretend that makes sense, and let's actually look at some interesting math there. Yeah, Jesus.
Professor,
I can hear you, but you're coming in and out.
oh, is it my mic?
Yeah, your mic's a little weird, but what's up? We'll do the best we can.
All right, quick question. Filament, what does it mean? Sorry.
So, a filament like a light bulb filament or something like that. Just
Okay.
Yeah, just think of it as a source of charged particles. So let's not be completely wacky about this. So we're looking at forces, right? Hold on. Let's see what we can figure out here. So we know that the force of we have here, we know that the electric field, right? The electric force equal to Q times E. And we know the magnetic force is equal to whatchamacallit, QV B, basically, right? We're just, since everything's nice, we're just going to pretend the sine phi is 90, which it is in this case, and that'll be equal to 1. All right, so if we, let me see something here, because though I'm doing it in my head and it's all coming out 1, which is not good. I want to see this. Oh, it was up here. Come on. So okay, so I'm not wrong there. So you got QE. So now what we're interested in is the area in which these two things are equal, right? That will get the particle to go just straight through, and create a spot of light right at the center. So we can actually see, we can view where the spot of light is created, and that will tell us when our electric force is equal to our other force. Now we can take the ratio of E over B and set that equal, well, not setting it equal to anything. Let's actually compute it. So we have Q basically, we can set these equal to, hold on. We can set these equal to each other. That's when the spot's at the middle. And then we can solve for E over B is equal to V, right? You can just see the Q's will cancel out, and then you just solve for that. So if we look at this, if we look at the deflection, so in chapter 20, okay, so in chapter 22, if you look back, we derived pretty simply using kinematics and other things and forces a deflection term, right? Q times E L squared over 2mv squared. You can go back and look that up. And now if you plug in V here is equal to E over B, you can actually solve for the mass over charge ratio. You get M over Q is equal to BL squared over 2YE. And this is interesting because this is a classic physics equation. So your length and deflection, you saw in physics 1, you can measure even micrometers. So you can get your deflection and your length are easy to measure. 2 is just 2, and your electric fields and B fields are pretty easy to measure in the lab. What's hard to measure are electron charge and mass, particularly if you're talking about olden times. So what this apparatus allows you to do is you have a direct apparatus, right, that lets you look at the deflection, set at that point a ratio for E over B, which gives you V, and that will allow you to, at this point, using the deflection criteria, the deflection equation here, you can solve for, you can put that velocity back in as E over B and actually solve for the charge to mass to charge ratio. All right? So it's experiments like this and sort of simple theory that give you these fundamental insights into how the atomic nature of the universe. That's pretty cool. It might seem a little anticlimactic, but this is essentially a cathode ray, all right, connected to a vacuum pump with coils. And if you ever look at a cathode ray or one of your old TVs, this is kind of just how they work. So, you know, the TV was a great application. You know, you're all probably using it to pass the time in some way, or you're using definitely a version right now. You're not using anything like this unless you have a really old TV. TVs haven't worked like this in a while. But, you know, it's not just about creating fun pictures to watch. It's about understanding the structure of fundamental quantities in our universe. So it's pretty cool. And I didn't just want to give you the word barf. So I hope that you found that a little interesting. And yeah, and it's pretty straightforward steps. I mean, it was a little bit of hand waviness, but I think we did okay. Now I want to talk about the Hall effect. I could even write it up here. So the Hall effect is what we use to determine that charge carriers are fundamentally negative. Now we have a negative charge carrier here, so I think it's just going to work. But let's go through the process. Okay? So basically, we can use, in addition to determining the nature of charge carriers, we can measure the number of carriers per unit volume of the conduction. So that's another result we can use. So let's take a look here at what's going on. So we have this charged particle, right, in a magnetic field. Now, if it has some drift velocity up, which we know it does, because there's a current acting on it. So again, the current will go the opposite direction. We'll notice that we're going to get a magnetic field B. So basically, all of these electrons will start to clump up on this side due to that magnetic force. Now that will induce an electric charge to build up on the other side of the wire. All right, and that will start to build an electric field, which will give you an electric force that that cancels out the magnetic field, leaving the particle after a short while, these electrons, to just move straight in the wire. Okay? Now, spooky. Yeah, no, I know. So now what's going to happen is once you do this, once you have this E built up, you actually have a potential difference across the wire. All right? And so basically what happened is when they first thought there were, I just want to make sure I'm not missing anything, another step. I don't think I am. Thursdays are rough days. So when we have this, buildup, we'll have a potential difference on each side of the wire that will create what we call the Hall voltage. All right, and the Hall voltage we can actually use a voltmeter and measure it. And what happened is that when you assume the charge carriers are positive and you set it up, you get a negative voltage, and that lets you know that you're not measuring the right charge carriers. So it was like, why am I getting a negative voltage? And then once you do it, you redo all the steps, you find that actually it's the negative charge carrier that gives you the correct voltage, where when you put the high terminal to low terminal, you get a correct voltage. So basically, when you have the proton moving, you get negatives. You expect the high terminal voltage to be on the other side, but it's on one side, but it's actually on the other. But with the electron here, if you were to measure just straight up, you would see that you get the correct voltage. And that's how the Hall effect tells us that charge carriers are actually negative instead of positive, which is pretty cool. Now, when we look down here, we can see the interesting conclusions. We won't be as thorough with that, but the number of charge carriers can be found in terms of the magnetic field and the volume of the no, this is not the volume, this is the voltage. And the voltage of the, too many V's today. And the voltage, the Hall voltage. And yeah. And you can find that Hall voltage here. So I'm feeling like I'm missing something. That's why I'm weird, because I love this. This is a great effect. There's a lot of good stuff happening here. But I feel like I'm not telling you something. But I think I told you everything. So anyway, I think when I used to do this, I used to have a positive one that I do to show you what happens with the positive carrier. So let's go down and see if we can do that. Let's see if that'll give us any insight. So let's do the experiment where we have the right result here, right? But let's do one where we're in the same magnetic field, so I'm not going to redraw the X's. But let's say we have a positive charge carrier, right? And we know we have a current going down this way, right? So we have we're going to assume what we know is incorrect. So we're going to say, oh, well, that's has some drift velocity going down that way. All right. So when we look at this, whatchamacallit, when we look at it positively, basically the positive ones are going to start building up. We have to figure out where the we have to figure out F equals QV cross B. We have to figure out the direction of the magnetic field. QV cross B. And so that is going to mean that, so we have V is down and B is in. So down and in. Hold on, now because I think our force is going to point the opposite direction. So we go where velocity is down and our magnetic field is in, so we point this way. This is interesting. The game is afoot. All right. And then, so our positive ones clump up here. And our negatives clump up here, right, to create that charge. That Fe charge to oppose Fb. Okay? And interestingly, yeah, no, because they'll go, that works. So interestingly, you'll note that if you do this experiment, this is what you would expect. You'd put your, now I don't feel so this must have been what I felt was missing, because this is, and now I feel complete. So if you put your high terminal here, right, your red terminal here, and in reality, in your low terminal here, you get a negative voltage. And so you're like, what? That can't be right. Why do I get a negative voltage? So because you get when you switch them, you'll get the right voltage. And you can see here that that will rule out our assumption must be false. And you can see here that with the current, we know that if we assume a negative charge carrier, our rules of electrostatics already tell us that the velocity must be in the opposite direction. That's a given. You can't have a negative charge go in the same direction as the current. That doesn't work that way, because we have both negative and we do know that we have negative and positive charges. So what's going to happen is V cross B, when we take it, is going to be in this direction. Okay, poor choice of color. It's going to be in this direction, but then because the charge is negative, we have to flip it, right? So we end up with this direction. And so what's interesting here about the Hall effect is that no matter what charge carrier we have, F dot B or FB should be pointing to the right. Doesn't matter which way it is. And then with that being said, we can definitively, using our voltmeters, determine that the charge carriers, because of the sign of our reading, must be negative. Now I feel good about the Hall effect and happy, ruffling my feathers. Okay? Kind of neat, huh? Well, maybe I'm the only one. Nice try, Jesus. No, I hear you. It's a lot to look at. That's why I like doing the wrong version of it. So okay, so if we're lost, what are we lost with? What do we want to look at? It's okay to stop and talk. I'm not in a rush. Everything? Well, you should have said something 20 minutes ago. I don't know. I don't know where we are now. Where should I start? Well, let's do everything with the Hall effect, because the thing we saw before with the canceling tubes was kind of fun, but there's some important ideas I think to understand that we'll go over the basics of. So let's do that up here with our blank slides. And let's see if I can summarize it, and maybe it will start to click. Or it could be a flaming pile of dog do. Hopefully not the latter. We're going to root for it. So let's delete everything and sort of start again. Maybe that's all right. So we have, in these sort of crossed field things where we're looking at stuff, we need to not only remember that we're dealing with magnetic fields, right? Where FB equals QV cross B. We're also dealing with electric fields. Right, and in the last instance too. Now, to give just a little bit of a review, right? For electric fields, the force, the direction will depend on the value of the charge. Well, I'm not going to write that down. Hold on. The direction of the field will depend on the charge, right? So if you have a positive charge, the force will go in the same direction as the field. And if you have a negative charge, the force will go in the opposite direction of the field. Okay, so we're good there. Now, let's go to the magnetic field, because that one is a little harder. In order to get the magnitude is pretty simple, right? The magnitude of FB, that's just going to equal QV B sine phi. I just stuck the B in there because I forgot it. But right, we have those 3 times sine phi. But in these situations, it's just going to equal QVB, because phi will be equal to 90 in these cross field situations. All right, so we're not even going to worry about it. The direction of FB is not trivial and is difficult. So we first have to do, so in order to find the direction, we first have to use the right-hand rule. To find the direction of V cross B. That's the first step. Then 2, we have to see what we have to look at sign of charge. All right, so if I'm looking at the sign of the charge, if it's positive, I'm done, right? Then if it's positive, then the direction of V cross B will just be the direction of FB, right? If it's negative, then we have to pick it up and flip it. All right, so that's where finding the direction of FB can be a little tricky. All right, so even though it's already written here, I want to do the same problem I did last time with the Hall effect. So I want you to notice we have a current and we have a magnetic field. The magnetic field lines are given here, right? They're going into the page. So do you see that? Do you see where the magnetic field is? Good. All right. So I'm going to delete those because they'll just get confusing, the circles, but I wanted to point them out. Okay, so we see where the magnetic field is, and I'm going to do it from scratch for the positive charge, so that we can get a real good feeling for what's going on. All right, so we want to set up the givens. So we know we want the current going the same way. We don't want to change anything in the problem. I'm not going to redraw, so there's magnetic fields, but can you just imagine they're there? Or do you want me to draw them there? Is that going to cause confusion? Or are you with me? I'll draw them in another color. I'll draw them quickly in another color. I'll make 9 of them. Just this way so we can see it. So now I'm going to go to blue, and now I'm going to, no, bad. It's not listening. So now I'm going to go to pencil and blue. All right. So let's make a positive charge. Now, this is incorrect, but we're going to pretend we're in the 19th century, right? We don't know any better. We're Ben Franklin's buddy. We're just assuming that the positive charge, that the charge carriers are positive. Okay. So what we're going to do is we're going to model it first, and then test it. So now, if I have a positive charge, just ignore the correct stuff for now. If I have the positive charge, right, and I know which way my current's going, I must have a drift velocity vector pointing down. Okay? And right now, I'm just in a magnetic field. So I know that V is in the negative, I know that V is in the negative Y direction, and X, or the magnetic field, is in the negative Z direction, right? So I have, if it helps, I have negative J hat cross negative K hat. Okay? And so when I look and I just do that, I get the negatives will cancel because of the cross product. So this will be equal to J hat cross K hat. They're identical. And J hat cross K hat, I know that's equal to I hat. So that's 1. This is the direction of V cross B, right? I just did some math to make my life easier. Now I'm going to look at the charge of my sign. So that means that FB, which I'll do in purple, no. Well, I'm going to hope I'm right, because once I have this, I look at the sign. If it's positive, which it is, then I'm done. I have the direction. If it were negative, I'd have to flip I'd have to flip the direction, but I don't. So I'm good. All right. So I have this force acting on the positive charges. Now, given enough time, those positive charges. So, well, first of all, are we okay where we're with FB? All right. Jesus, you still completely lost? And everyone else, you good? All right. So now, good. So now what happens is, as we go forward, these positive charges, I'm going to go back to blue. I do like my color selection on this thing. The positive charges are going to build up along the side of the wall. Okay? And that's going to lead to the inducement of negative charges building up along this side of the wall. All right, and the electric field will go from positive to negative, or from higher potential to lower potential, right? And that will build up until you have, basically you'll have FE. This process happens until you have an electric field that balances out your magnetic field. Okay, and that's what creates this Hall voltage. You'll notice that you have a potential difference from one end to the other. Okay, and so from here, if we have a voltmeter, right? So from here, basically what we expect to happen is that we will, when we measure this from here, and I'll make a voltmeter box here, and then we have a red lead and our black lead, right? We expect the reading on this voltmeter to be positive if we've done everything correctly. The interesting thing is that when you actually read it, it's negative. The reality is you would expect, your theory of positive charge carriers says that you should measure a positive voltage here. But when you put the voltmeter to the test, you get the voltage you were expecting, but it's negative. So what that means is that your initial assumption is incorrect. The charge carrier is not positive. So now you look at the situation, right? Now we can look at the situation. Well, now let's do the assumption of a negative charge carrier to show that we get the right thing. And you'll notice here that there's an interesting commonality between the negative and positive case, which is that FB goes the same direction, whether it's a negative or positive charge carrier. You have to remember that the drift velocity for negative charge requires it to go against the current. So are you good there? Has everyone got that part? We're good there? Okay. And then, so in this sense, when we find V cross B, hold on. When we calculate V cross, oh no. Failed by the pen yet again. All right, yep, bad. First, we just want the direction of V cross B, right? So V, put our hands up, crossed into B, and we get that the direction, this is V cross B. But we have to ask ourselves now, is the charge positive? If the charge is positive, we just leave it be. If the charge is negative, we have to flip this around. And you'll notice that that's where you get this direction from. So I'm going to delete this off the picture because since the charge is negative, we flip that around and we get this V dot B. And so now what happens, what you can see in the next picture, right, is that it's the electrons that build up on this side. And the positives build up on the other side to create the electric field, right, that balances out FB. And I want you to notice something. Now if you hook up the electrodes, like you do here, everything makes sense, because if you have put your red one here and your black one here, you'll get a negative voltage, and that's what the theory predicts with negative charge carriers. And it also predicts the correct high potential side. And if you put your high potential lead onto this side, you get a positive voltage. And that's how the Hall effect tells us or shows us that charge carriers must be negative in our electronics. Kind of cool, huh? Does it make sense now? Or are you at least less lost? Good. Good. Good, good. Magnetic fields are confusing. I think it's instructive to do it as many times as we need to do it. And plus, like I said, the blood sugar wasn't the best today, so it's likely that I will flounder a little. So, all right, cool. Let us move on to more magnetic fun. Actually, it's 7 o'clock. Let's take a break because we went with the explanation. We went a little past where I would have liked to go on for break. So let's take a break until around 7:15, and then we'll sort of wrap up a little bit with a little more magnetic fields. And we're almost certainly going to pick this up on Tuesday of next week when we reconvene to to go over this chapter. I wanna take our time if we can a little bit with the magnetic fields because there's a lot going on. So I'm gonna go away from the computer for a little bit, get some water, get something to drink, and then we'll be back and we'll continue. Don't be, if we have questions too, we'll start when I come back. I'll start and ask if there are any questions. So don't be afraid to ask and have us go over something, or me go over something. Hold on. Okie dokie. Oh, I forgot the light. Hold on. It's getting dark. Oh, Jesus. There we go. All right. So, any questions while we were on break? Anyone come up with anything? Anybody? All right, we're going to move on. So, you've had 15 minutes to look at this. Still processing, trying to get back to go back at the textbook. Yeah, no, there's a lot of good stuff to read here, actually. Yes, Chewy, that is a very important point and part of the definition. Magnetic fields only exist with moving charges. And that actually has a lot of applications also to special relativity when we try to look at electromagnetic radiation in Galilean frames. It doesn't work because in one frame there is a magnetic field and in one there isn't. So no, magnetic fields require moving charges. In permanent magnets, you might ask, well, where's the charge? Remember I said those are hard to describe. That's where you start needing intrinsic magnetic charge, and that comes in quantum physics. So what you could do, they were able to know that permanent magnets was a similar phenomenon to, or those magnetic fields were at least of the same kind of equivalence because they behaved the same as the current carrying magnetic fields. And it's too bad we're not in class because we actually have demonstrations where you can just run current through wires and stuff and see that it has a magnetic field. It's pretty easy to see. But alas, it wasn't meant to be in the spring of 2020. So good. Other questions, complaints? We're good? All right. So we want to go to circulating charged particles. So we're actually going to be able to build up a few things here. So let's just look at our picture here. The word vomit will be nice. Basically, we're seeing a charged particle move in a circle. All right, so the magnetic field, if you'll notice here, is keeping it in a circle, and the angle between V and B is 90 degrees. So if we go up to we can write that FB, right, will be equal to QVB, right, where we're going to use the absolute value sign. But you'll notice that in the picture, the inward force, FB, is causing a circular motion. So we can set that equal to mv squared over r. All right, and so we can solve for the radius. There's one interesting thing we can solve for. Right, so this implies all you have to do is solve the algebra that r, or I have that as big R over here. I'll change that. That's just going to be confusing. I'm just relabeling to little r. So we know that the radius will be equal to mv over qb. And that's pretty cool. That will give us the radius of a circle, so we can actually design how big our circle would be with these parameters. All right. And now what could also be pretty good is if we're moving around in a circle, You'll recall from physics 1 that the period of motion is equal to, I believe it's 2 pi r over v. And you can just plug in r, so that will be equal to 2 pi over v times m v over qb, right? And those v's cancel. And of course, if you do that, you get the frequency, right? F equals 1 over t will be equal to qb over 2 pi m. All right, and these are important things because what we're looking at when we looked at curved motion is this will bring us to some pretty exciting physical instruments. But we want to be able to know those properties from our distance. Now, there's an example I would usually like to go over. I just wasn't able to fit it in time, but let's see if I can. It doesn't usually like me to share the screen. I tried to put it in during break, but I needed to do some other things. I'm not going to do the full example, but I am going to try and get you the draw the picture. So I'm going to go to the blackboard, and I just want to describe how the object works without going over too much, the formal example. So one share blank whiteboard. So what we want to look at is an object called a mass spectrometer. All right, and we have basically our chamber. Oh, wait a minute. Ooh, I need boxes. Hold on. And lines. Forgot lines could make this work. So I need a box. I need a chamber box. I need a source box. And let's see here. We need openings in these boxes. All right. And then we need wires. Wires are so we'll have something like this. We'll have our negative terminal. We'll have our positive terminal. This isn't actually turned out half bad. I mean, it's not great, don't get me wrong, but it's not terrible either. And let's face it, everybody, if I had to draw this on the board, it wouldn't work out very well. It would be a disaster. So we have here a source of ions. So we'll diagram it out. Ionic source. And the battery keeps it at a potential difference, V. All right, and we're going to have a detector here. That's fine. And we're going to have a magnetic field coming out of the board. So I'm going to make dots. I'll make a few of them. Again, when you're doing this by hand, you have to be So basically we have a setup here where we're firing positive ions into this chamber, okay? So the problem reads, so basically so this is a mass spectrometer, all right? And basically if you're given the voltage, you know that they're an ionic charge, so you know Q. And you know the magnetic field. Now the two unknowns are the mass and the distance and the detector. Okay, so you'll be measuring the position x that you hit. So now let me ask you, which one of these things do you think is easier to measure? Which one of these things do you think is if you had to measure one, whether you're measuring an atomic, the mass of some atom, or the position in that detector? Which one? If I gave you a summer to measure one of those things, which one would you pick? You're going to make the same $5,000, but you have to get one of those measurements done. The position, right? Yeah. No, you're absolutely. You are not going to choose to just come up with that magnet and get the position. So we're going to move the position to the known column. So then you'd measure position. And if you can measure that position and you know these other three quantities, you can look at the path of an atom, and basically, right, you're shooting the ion, and as the ion comes in, it'll start to curve. And that's what we saw. What would happen is you go in, you start to curve around, and then you'll land somewhere on that detector at some position x. And basically what this apparatus does is it lets us look at the mass. All right. So when we look at this, we want to look at and be, we want to remember sort of what we were, if we want to find that mass, we want to look at what we know about circular charges. So we know that the radius of that circle, right? So this will be hold on, yeah. I want to make a box around our givens. So we know that the radius of that circle, right, is equal to mv over qb, right? So it's tempting. Hold on. Let me see something. They gave us r at x. Okay. So yes, the radius would be x over 2. But now we have two unknowns here, right? So r is equal to x over 2, or x equals 2r. Either way you want to look at it. Right, so basically, if this is a circle, which is not a very good one, and I will give you that, right, x will just be the diameter of the circle, the semicircle. So that means that the radius of the circle is x over 2. Okay? Now, what we don't know here, because we know r, we know q, and we know b. Now, mass is what we want. But we also have, we've got voltage, we've got a V, but that's voltage, right? This is voltage. This V is speed. So now we know we want M, so we got to do something about V, all right? And the way to do that is to realize that is we can conserve mechanical energy, right? Because we have, as we go through here, we conserve mechanical energy going sort of through here, through our part here. We're converting electrical energy to potential energy. So we have delta K plus delta U. And of course, this is the change. If the mechanical energy is conserved, that will be 0. But let's take a look at what's going on here. And this is hard because I think it would take a while to sort of say, oh, we'll just use energy conservation. But basically, what's happening is that without the potential voltage, without the potential difference, the ions just stay here. The charge difference, you're storing the charge in the battery, so that's QV. So the potential change here will go from, or will be minus QV, and the kinetic energy is always just, is going from 0 to 1/2 mv squared. So when you look at U, so K initial, let's look at kinetic energy. So when you get right into the entrance, your kinetic energy is 1/2 mv squared minus, and then you're at your source, it's 0. You're accelerated. And so what that means is if you look at the U part here, your initial energy, your initial potential energy is QV, and then you minus to 0 there, and then you have your negative here. So when you put that in, it'll be 1/2 mv squared minus QV. This is the weird part. I'd suggest if you want clarification here on our conservation of mechanical energy part, I'd say look at the book. But I'll read you what it says. So we know that we lack the ion's speed, so we need that. To relate V, our speed and our voltage, we use the fact that the mechanical energy is conserved during the acceleration. So when the ion emerges from the source, its kinetic energy is approximately 0. So we already had that here, right? And at the end, it's MV. That part I think is easy. Also, during the acceleration, the positive ion moves through a change in potential minus delta V. So thus, because the ion has a positive charge, its potential energy changes by minus QV. Okay? So we have that. So that's the explanation for where the minus comes from. So once you look all that and that makes sense, we have this is our mechanical energy conservation, and as you can see, that's going to equal 0. That's the easy part, right? Because the mechanical energy is conserved. And now you can solve for V, which I'm going to do up here. So the speed is equal to square root, or not the square root, but I mean, it is the square root, but you guys know I prefer to write it as 2Q voltage. This is going to be a Q. Hold on. No, that's the wrong thing. All right, over M. And that's going to be to the 1/2 power. Same thing as the square root. Okay, so now basically you can plug both of these into your equations, and you can do some algebra, and you can solve for the mass, which would be equal to b squared qx squared in terms of givens over 8 times the voltage. Okay? So basically, the idea here is that you can actually measure masses at the atomic scale with this type of apparatus. Again, knowing the fundamental charge, that's the one hard thing you have to know. But if you know that fundamental charge, you can measure any atomic mass, all sorts of different atomic masses, right? By measuring the magnetic field, which is macroscopic, the length, which is macroscopic, and the voltage, which is macroscopic. All right. And for the particular example, they had values of the voltage was 1,000 volts, which you can measure. An 80 millitesla magnetic field is easy to measure. And a distance of 1.6254 meters is easy to measure. Hard with that precision, but easy enough to do. And of course, we know we could use the known charge from other things. We need a few more significant figures to get the atomic masses. But basically what we do is that electrical energy, you're going through this, basically you're looking at an ion, and you're sort of looking at it going through to be accelerated, going the opposite way. That's why they say a negative potential difference. So if you were to use the half loop law, if you will, to go around, you could say that you're going through here, but then this is the source, and then you go through this potential to get that ion to move up this way. All right, and so that's where you have the potential energy. The change in potential energy would be minus QV going through here, and that minus QV potential change would lead to going from 0 kinetic energy to all kinetic energy up here. And then using energy conservation, that lets you solve for the speed. And then once you have the speed, you can plug that back in here, and you have everything, right? And you can solve for M. And this is where you get, and then when you solve for M, you get this expression. And that lets you measure, so the significance here, the importance of talking about this is that we have now designed and looked at a device with macroscopic measurements that lets us measure atomic mass at the atomic scale, which I think is pretty darn cool. And these mass spectrometers have all sorts of uses. In fact, one of the more interesting ones I've heard of is, if you remember the anthrax attacks back after the September 11th attacks. I don't know if you guys are too young for that one. Some of you aren't, I know, but a few of you might be at this point now. When I started teaching 8 years ago, everyone remembered. But they were able to actually use mass spectrometers to get a, yeah, people are getting it in the mail. Yeah, that's right, Mustafa. They were actually able to get a conviction because they were able to use mass spectrometry, a very sophisticated mass spectrometer to figure out the location of the anthrax, and then the people who had access to it. And there was only, once they did it, figure that out, there was exactly one person who had access to that anthrax, and no one else could have possibly done it. Like entered the room and gotten into all the places. So it's pretty interesting. So mass spectroscopy has been used to solve crimes, and big ones. And it's a very fascinating field, and it's used in precision measurement all the time. So that's kind of the exciting thing here. It's not so much that this chapter, I think, as you're seeing, is a little more experimental than theoretical as far as interest. It's like the theory is okay, and we talked a little bit about it, but it's the applications of what combining a magnetic field with an electric field or a source. It opens up a whole new scale of the universe. And I mean, there's tons of stuff you do with the interplay of electric and magnetic fields. You can do things like scanning electron microscope, scanning tunneling electron microscope images. I mean, all this stuff are compound circuits, and a lot of them do make use of things like semiconductors. But you can do a lot. I mean, it's pretty spectacular, the things we can measure and see by combining these types of technologies. So again, I hope that was interesting. If it might not make sense in terms of the overall theory, but in talking about the J.J. Thomson apparatus, the Hall effect, and now the mass spectrometer, you can see that this really is an applied chapter. We're talking about how to measure things, which is fundamentally what we do in physics, right? Precision measurement is a big part of the subject of physics. So I'll leave this up for about another 10 seconds, see if anyone's got anything on it. And then I want to move on to cyclotrons and synchrotrons, and I have a feeling that covering that will probably bring us Not to the end of the chapter, because I'd like to sort of get back to theory by the end of the chapter, which it does, but I think we can cover some interesting stuff and get up to there by our 7:55 end time mark. So yeah, so see if you have any thoughts on that or questions. And this example is in the book if you want to look it up. It's pretty good. And let's see. Okay. That's the change in potential energy, right? It underwent a let's see, was that correct? I might have messed up the order there. So if we start here, we start at 0, that's our initial energy, right? And then we get up to here. And then we start, so if we're here, we're at a potential. So we start here at a half, get down to 0, and then we do negative. So if we're here at 0, we should be at negative V here. And then all that negative V kinetic energy here, we should have 0 potential energy, right, going this way. And then so if we have 0 potential energy, I think I might have got that backwards. That's okay. Shit happens. I was trying to look at the change in U, okay? So, in fact, I've got the, let me make sure I do get it correct. Right, QV is the potential energy of the charged particle. So delta U equals, actually I think, because if we're looking at initially, we're at 0. So I think we start off, if our final kinetic energy, if in the final part we have all kinetic energy, that means, yeah, I messed it up. We have 0 here in the final, and then minus an initial potential energy of QV. All right, well, it's plus the minus. You think you get the idea there, but that's the initial potential energy, the final potential energy, right? And the final potential energy has to be 0 because the final kinetic energy is 1/2 mv squared, and the initial kinetic energy is 0. So yeah, those have to be in opposite places. So I bungled that up a little, but that's correct now. Yeah. Good. All right. So let's move on to cyclotrons. We got to go back to the shared file. Share files. And we're on chapter 28 with its glorious applications. So now we want to go to cyclotrons and synchrotrons, which are sort of our ultimate application. So let us do that. Let's make sure I'm not missing anything here. So with the cyclotron, it's a word barf thing, but we have a source and we have these two Ds, all right, these hemispherical Ds. And basically we have an oscillator here. So so as I think I've told you, I'm a theorist, so I love cyclotrons and synchrotrons, but I never remember how they work. I mean, I know it's basically a flipped signal to beat the electron to go faster and faster and faster, but let's look at the details. I have a lot of my experimental friends who are probably laughing at me now. The figure is a top view of the region of a cyclotron in which the particles circulate, all right? So basically you use them to go from one end of the D to the other to go faster and faster and faster. So the two hollow D-shaped objects are made of sheet copper, These Ds, as they are called, are part of an electrical oscillator that alternates the electric potential difference across the gap between the Ds, right? So that you can oscillate this, you can modulate the oscillation frequency of the cyclotron. The electrical signals of the Ds are alternated so that the field in the gap alternates in direction, first towards one, then the other, back and forth. The Ds are immersed in a large magnetic field directed out of the plane. So you can see there's this field here that keeps the circular motion going. The magnitude is set via, it can be modulated as well. And the key to the operation is that you don't want to just pick a random frequency. You want to design your cyclotron and run it at a resonant frequency so that they don't start and stop, but that they keep going faster and faster continuously around. And if you're at a resonance frequency, the cyclotron accelerates the particles faster and faster and faster. Now, this is important because when you're doing something as fundamental as particle physics, and you want to look at particles at higher energy, you need to accelerate them using a cyclotron or a synchrotron. And when you do this, you can, let's see, do they have you get a particle beam. And if you create a target for the particle beam, you can smash the high energy particles into things and get tracks. And that's how you measure, these weird circular tracks. They kind of look like this a little bit. Basically a collision. You'll have one particle sort of spiral out like that. You'll have another one spiral out or they spiral outward. They do weird stuff. This is how particle colliders work. A particle collider is a cyclotron or a synchrotron. And so you can use these particle beams to measure, you can use, basically new particles can be created in these high energy collisions, and that's how we discover new particles. And so, again, the cool thing is that basically the building these things and tuning them is very difficult. The fundamental physics behind them is not super hard, but the stuff you can learn is pretty amazing. Now, the synchrotron is the proton synchrotron. The magnetic field of the oscillator frequency, instead of having fixed values like they have in the cyclotron, are made to vary with time during the acceleration cycle. All right, and what that means is that when this is properly done, the frequency of the circulating protons remains in step with the oscillator at all times, and the protons follow a circular and not a spiral path. So this means the magnet need to extend only along the circular path and not over the entire area of the cyclotron. So the circular path, however, must still be very large if high energies are to be achieved. And so if you look at the Large Hadron Collider, the Large Hadron Collider is the largest such device, synchrotron device in this setup, and that has a circumference of about 30 or 40 kilometers, I believe. It is the most expensive and one of the most precise instruments ever built, and that's the instrument they use to find things like the Higgs boson and test the standard model of physics. So to test at these types of instruments are used to really peer at the very edge of our understanding of the universe, and they're very cool. I wish we could. In order to go deeper into they're not looking for antimatter. Antimatter is created in these reactions and measured fairly readily. You don't create much of it, but it's there. Antimatter is not a theoretical construct. It's very much been found and discovered. They're trying to find new particles they've never seen before and stuff like this. But yeah, if you want to create antimatter, you have to use a cyclotron or a synchrotron. Yeah. No, it is cool. I agree concurrently. I concur. So why don't we create antimatter coronavirus? I don't know. Well, the truth is it's really difficult to create antimatter. You don't get a lot of yield, if you know what that means. And yes, this is the Higgs boson stuff. So the Higgs boson, you just need a larger loop gives you more energies. And the what particle physics does is I'm getting there. I can only do one at a time. With the with the what was the last question? Yeah. So basically, the standard model of particle physics predicts the energies at which these objects, like the Higgs boson, exist. So you had to build a ring large enough, like this Large Hadron Collider, and that's what allowed you, when it was built, it was finally at the energy, large enough to be able to detect a lot of these predicted values of the Higgs boson for small variations in the standard model, and they found it. Antimatter is really dangerous, and you store antimatter magnetically. So it's very vital that you that matter not come into contact with antimatter, because if you have just 1 kilogram of antimatter and 1 kilogram of matter, so if they came together, they would make an explosion that had a yield of E equals mc squared. And that would be 1 times 1, or that would be, the mass would be 2 times 9 times 10 to the 16. And that would be 18, so 1.8 times 10 to the 17 joules. Now that might not mean much, but megaton. So, but that would be equal to about, let me look on my calculator here. Let me see. Hold on. I'm going to use my phone. Oh, I'm on the calculator. Hold on. So 1.8, 1, 8, 2, 3, 4, 5, 6, 7, 8, 9. Oh, crap. It won't do it. 1.8 e to the 17 divided by 4.184 e to the 15 equals. So it would basically be a 43 megaton explosion, which would be equal to among the largest thermonuclear bombs ever let off. So that's just 2 kilograms of matter, or 1 kilogram of matter coming in with 1 kilogram of antimatter, which isn't a lot. So no, it is not playing. It's not playing at all. So 16, 17. Yeah. So all right. So I think that will, and what about creating mini black holes? So mini black holes I've always thought was a bit ridiculous, because everything we know, even if we did create them, they wouldn't be that big of a deal. One, black holes are not forever and they evaporate, and the smaller they are, the faster they evaporate. So even if we could create a black hole, I don't think it would exist long enough to really harm us. And two, it would still have low mass, and so all of the energy would have to, I mean, the energy required would be spectacular and have to have access to length scales that I think are beyond quantum physics. I think the danger of creating a mini black hole is exactly none in one of those things. But of course, I can say that, Mustafa, because if we do create a black hole and all die, no one will be around to prove me wrong, now will they? But yeah, but seriously though, I don't think it. It's not a realistic concern. The energy, you can calculate the energies needed to create black holes that would last long enough to be of real harm, and I think they far exceed anything. If we create, it's more likely that those same black holes would be created in the atmosphere with collisions with high energy particle rays, because they're cosmic rays that are much more energetic than anything we see in the Large Hadron Collider. So essentially, if that were an issue of the Large Hadron Collider, nature would have killed us a long time ago by creating black holes when these cosmic rays hit our atmosphere. Yeah. No, we're good. They may mess around. Someone may mess around and kill us all, but it won't be via black holes. At least not yet. All right, I'm going to take a picture of the attendance, and in Sweden they have created, no, there's no black hole in Sweden. I know that they might like to think there is, but there is not. No, a man-made black hole would be virtually infinite energy. It would be pretty spectacular.